So next step is calculation of factored moments. Okay, so because of the upward pressure, moment will act in the footing portion only. Okay, so the footing will be a cantilever, will be act like a cantilever beam. Okay, so the column is in the center of the footing only. So the remaining portions are behave like a cantilever. Okay, so first the cantilever projection from the short side face of the column. Okay, so short side face of the column, column size is 300 by 500 and the footing size is 2 meter by 3 meter. Okay, so in this the short side is 2 meter. Okay, short side of footing is 2 meter. Okay, long side of footing is 3 meter. Okay, so 2 minus, okay, 2 minus uh, yeah, I'll show it in a diagram. Wait for me. Okay, so the size of footing is, that it is clear or not? 2 meter by 3 meter. So long side is 3 meter and short side is 2 meter. Okay. The diagram is clear for you guys. Kadir,
சார்
diagram clear இருக்கா?
சார் ஓவரலோ கிளியரா இருக்கு சார். இல்லைன்னா வரைஞ்சிட்டு வேணா மொத்தமா போட்டோ எடுத்து வேணா காமிங்க சார். வீடியோக்கெல்லாம் ரொம்ப இதா இப்போ சார் கிளியரா இருக்கு.
Okay. Okay. Footing size on the 2 meter by 3 meter. In that we are having a column at the center. Okay. So the size of the column is 300 by 500 Okay. So 300 is the short side. So 0.3 meter. 300 means 0.3 meter and 500 means 0.5 meter. Okay. So this portion is the cantilever portion. Similarly, here also cantilever, and this side also. This one is the cantilever portion. Okay. So total width of the footing is 2 meter. Okay. So 2 minus 0.5. 2 minus 0.5. That is equal to, sorry, 2 is the height. That is okay. This is 2 meter, and this one is 3. Okay. Okay. 3 minus 0.5. Okay. Actually, the width of the column is 0.5 meter only. No. So 3 minus 0.5. Okay. Out of this 3, this 0.5 is gone. Okay. So 3 minus 0.5 means we are getting the value as 2.5. Okay. So in this 2.5, half of the distance will share to this left side and the remaining half will transfer to the right side. So 2.5 5 divided by 2, 1.25 meter. Okay. Similarly, in height wise also 2 minus 0.3. 2 minus 0.3, that is equal to 1.7. So 1.7 divided by 2. Okay. So half of the distance will transfer to the top side and remaining half will transfer to the bottom side. Okay. So 1.7 divided by 2 is equal to 0.85. Okay. So this length is 0.85 meter and similarly this one is 0.85 and 1.25 is the left side and the right side. Okay, the cantilever projection is 1.25 meter in left and right sides are 1.25 meter, and in top and bottom sides are 0.85 meter. Whether you guys are seeing the slide? Okay, so step number 6 is calculation of factored movements. Okay, so cantilever projection from the short side face of the wall. Okay, that only they explained here. Okay, 0.5 is the 1 by 2. Okay, so 3 minus 0.5. So 3 minus 0.5 is 2.5. So 2.5 divided by 2 means 1.25 meter to both sides of the column. Okay, in short side. Okay. Similarly, cantilever projection from the long side face of the column. Okay, from the long side. Okay. So 2 meter will come. So 2 minus 0.3. 0.3 meters the size of the column. Okay, so 2 minus 0.3, 1.7. So 1.7 divided by 2, 0.85 on either side of the column. Okay, so have you understood these two tips? Okay, 1.25 meter and 0.85 meter. So after this, after calculating the projection length and all, cantilever projection length on either sides of the on all four sides of the column, the next step is now we are calculating the bending moments. Okay, so the load soil pressure will be like a UDL. Okay, so we are calculating the moment because of the UDL. So load into distance by 2. That is the formula for calculating moment because of UDL load. Okay, load into distance. So that is PU into L into L divided by 2. So 1 by 2 is nothing but 0.5. Okay, so they wrote the formula as 0.5 into PU into L square. Okay, so PU value is here 0.2505 Newton per mm square or 250.5 kilonewton per meter square. Okay, so 0.5 into 250.5 into length 1.25. Okay, in short side face of the column, the length is 1.25. So 1.25 square is equal to 195.7 kilonewton meter. Okay, so bending moment at the short side face of the column is okay 195.7 kilonewton meter. And next bending moment at the long side face of the column. Okay, so yes, the slide is changed. So bending moment at the long side face of the column is the same formula, zero point 0.5 into pu into L square. Okay, that is equal to 0.5 into pu value is 250.5 into L value is 0.85. Okay, so 0.85 square, and we are getting the bending moment value is 90.5 kilonewton meter. Okay, so after calculating the moments, okay, cantilever moments, the next step is calculation of depth of footing. Okay, so far we calculated the reinforcement for columns. Okay, after that we calculated the size of footing. Okay, in size of footing we calculated width and breadth only. Okay, the length and width only we calculated, we didn't calculate the depth. Okay, so next step is we are calculating the depth of footing. So we know the formula. Mu is equal to 0.138 FCK BD square. Okay, so by using this formula, we are calculating the depth of footing. D is equal to square root of Mu divided by 0.138 FCK B. Okay, so in this formula, we are calculating the depth as 266.3 mm. Okay, so after calculating the depth, next we are considering the shear factor also. Okay, so the critical section for one-way shear is located at a distance d from the face of the column. Okay, the critical section for one-way shear is located at a distance d. They'll ask this type of question in a 1 mark, maybe in government examination. At what distance the critical section of one-way shear occur in footing? Okay, so it has occurred at a distance d from the face of the column. Okay, so for shear force per meter width is equal to VUL is equal to 0.2505 into 10 power 3. Okay, we know the upward soil pressure, factored upward soil pressure as 250.5 kilonewton per meter square. Here they're substituting in Newton per mm square and they're converting into kilonewton into 1250 minus D. Okay, so 1250 is the load factored load. Okay, 1050 is this meter cantilever projection. Okay, 1.25 meters. Okay, they are substituting in mm, 1250 mm. Okay, so 1250 minus D. Okay, so therefore, assuming the shear strength of concrete tau c is equal to 0.36 for M20 grade concrete, and for this the percentage of reinforcement is 0.25. So therefore, tau c is equal to Vu L divided by BD. We know this formula and all. Okay, tau c is equal to Vu by BD. So tau c value only 0.36. Okay, so 0.36 is equal to VUL. VUL is this equation. Okay, 0.2505 into 10 power 3. Okay, we are substituting this in here. So 0.2505 into 10 power 3 into 1250 minus D divided by BD. Okay, so B for 1 meter length we are calculating, so 1000. Okay, 1000 mm into D. Okay, here we are getting, on solving this, we are getting the D as 513 mm. Okay, so D is nothing but effective depth. Okay, so two method is there. Okay, in first method we are getting the effective depth of 266.3, and in second case we are getting a 513 mm. Okay, so we are choosing this value, second one. Okay, so hence adopt effective depth as 550 mm. Okay, we are rounding this value to 550, so hence adopt effective depth as 550 mm, and the overall depth D, capital D, as 600 mm. That means the effective cover is 50 mm. Okay, 550 plus 50 is equal to 600 mm. Okay, so after calculating the depth of footing, okay, after calculating the depth of footing, the next step is reinforcements in footing. Okay, so reinforcements in footing in longer direction, shorter direction. Okay, so longer direction is 3 meter. Okay, the size of footing is 3 meter by 2 meter, 2 meter by 3 meter. So shorter direction is 2 meter and longer direction is 3 meter. Okay, so in longer direction, the formula mu is equal to 0.87 f5 AST D into 1 minus AST f5. We know, all know this formula. Okay, so mu value is longer direction, the moment is 195.7 into 10 power 6. Okay, is equal to 0.87 f5 value 415 into AST. D value is effective depth, which shows the effective depth as 550. So 550 into 1 minus AST f5. AST f5 value 415 divided by 1000 into 550 into 20. Okay, so on solving this, we are getting AST as 1029 mm square. Okay, so we are providing 16 mm dia bars at 160 mm center to center. So for this, we are getting AST as 1257 mm square. Okay, which is more than 1029 mm square. Hence, it is okay. Okay, so we are choosing 16 mm dia. So for 16 mm dia bar, the area is 5 into 16 square by 4. Okay, so we'll get the area as 201 point something, 201.2 or something. Okay, area 201 mm square. So for 1 meter length only we are calculating. Okay, so 1 meter length means 1000. Okay, 1000 mm. So 1000 divided by 160. Okay, yeah, they're providing six spacing as a 160. Okay, so 1000 divided by 160, or we will add the effective cover also. Effective cover 50 means 1000 minus 50, 950. Okay, so 950 divided by 160 means we'll get the value as a 6 point something. Okay, so 6 into 6 point 201 point something means we'll get the EST as 1057 mm square. Okay, so after calculating the reinforcement for longer direction, next we are calculating for shorter direction. Okay, so for shorter direction, the moment is 90.5 kilonewton meter. Okay, we already calculated this moment value and all. Okay, so 90.5 into 10 per 6 Newton mm is equal to 0.87 FI ASTD. We are using all those data. Okay, and we are getting the AST as 468 mm square. Okay, so in shorter direction, on solving the moment formula, we are getting the AST as 468 mm square. Okay, so after that, ratio of long to short side. Okay, so longer side of the footing is 3 meter and shorter side of footing is 2 meter. So ratio of longer to short, so 3 by 2, so 3 meter by 2 meter, we are getting as 1.5. Okay, we are naming that ratio as beta. So beta is equal to 1.5. So after calculating that ratio, we have to check. Okay, we have to calculate the reinforcement in central bandwidth of 2 meter. Okay, so it is in IS 456 2000 as per class 34.3.1. We have a formula. Okay, 2 divided by beta plus 1. Okay, so beta only we calculated, beta value is 1.5. Okay, so into AST. Okay, so 2 divided by 1.5 plus 1 into 2 into 465, 468. Okay, the reinforcement we calculated is 468. Okay, on shorter direction, AST value is 468 mm square. Okay, so we are using that also two times. Okay, reinforcement in central bandwidth of 2 meter. Okay, we have to multiply the AST into 2. Okay, so 2 divided by 1.5 plus 1 into 2 times of 468. So 2 into 468. So we are getting 749 mm square. Okay, so the minimum reinforcement. Okay, this is also area of reinforcement only. Okay, in previous case we are getting 468 mm square, and after that by using the central bandwidth formula and all, we are getting the area steel reinforcement as 749 mm square. And the next cases there is a formula for a minimum reinforcement. Okay, so the minimum reinforcement is 0.12 percentage of cross section. So 0.12 percentage means 0.0012 into BD. So 1000 into 600. 600 is the depth. Okay, depth of the footing. For footing only we are calculating. No. So in previous case itself we calculated the depth of footing. Overall depth is 600. Yeah, capital D is equal to 600 mm and small d effective depth as 550 mm. Okay, so 0.0012 into 2 into 1000 into 600. Okay, so we are getting for the area as 1440 mm square. Okay, in this case, by using minimum reinforcement formula, we are getting the minimum reinforcement as, okay, area steel reinforcement as 1440 mm square. okay, which is more than 749 mm square. Okay, but we are going for this formula itself, the central bandwidth value itself. Okay, that area of steel reinforcement is 749 mm square. Okay, we are going by that case itself. So we are providing 12 mm dia bars at 150 mm center to center. Okay, so for this, the area of steel reinforcement is 754 mm square. It is more than 749. Okay, hence okay.